Thank
So
you.
the last presentation is actually I'll be conducting that, and as you might see, I'm an assistant professor at Clemson, and my background starts with trying to understand structural behavior of systems under fire conditions, and I did a little bit of earthquake from there, and now we're trying to delve into the AI realm. So for this presentation, we're trying to showcase a few case studies where we can use what we call autonomous evaluation of fire damage concrete structures. So this presentation was done with my colleague Kevin Millar, the chair of ACI 216. Plus, we get a lot of help from the members of 216. So thank you for your participation. As you notice, which was a little bit interesting in this session, almost everybody started with what's AI, because we all kind of knew that this is it's a new technology and there is a lot of buzzing around it. But what I really want to emphasize in this talk is that AI is I would like you to think of it as a technique, just like what we do. We know how to do tests, we know how to do simulations. AI is another technique that we can leverage in our domains. And I'm pretty sure that you've heard about AI in material sciences, robotics, medicine. You can see that even like a very small example would be at Tesla. How driving is a very simple problem, but it's completely revolutionized by the use of Teslas. And if we can apply some of the techniques they use in this autonomous vehicles to concrete design or structural design, then we can have a lot of new ideas that we can make very, very cool stuff, as you'll see and have you seen earlier from my colleagues. So to start with with the AI problem, I like to show this chart. So you can see this is how we introduce automations into different domains. You can see agriculture, manufacturing, mining, construction. So since the 70s, there is a lot of push for automation plus AI, not just AI. And as you can see in agriculture, there is a lot of, I'm sorry, my dogs are barking in the back. There is a lot of interest that gaining a lot of total change, almost 16 times the amount of change when it comes to automation. In construction, unfortunately, it remains very, very small. And this brings in a new concept of, well, if we can use some of the advantages agriculture has seen, perhaps we can also have a lot of improvement in our domain. When it comes to publications, you would see that starting 1960s and onward, there is like a little bit of work. And since the 80s, there is a lot of work when it comes to AI, and almost there is more than 100,000 paper a year. And whenever there is publication, there is patent, because now people can understand that we can leverage this to have a lot of resources in there. And if you look at the numbers, there is a lot more than 100,000 papers. But if you look at structural engineering, and this is where it becomes, you can see a large gap, because now in structural engineering, we barely have almost 1% of the total number of publications when it comes to AI. So although we have some work done, in 2000s, even way before that, I think Henry mentioned like 80s or late 80s, but the numbers are very, very small. And as you can see here, there is a good trend going upward, and hopefully this trend will continue. And this trend showcases that the industry, academia, education is very interested in this domain. So hopefully we can go together towards that side. Also, as you have seen earlier, both Emilio and here did a great job of explaining what AI is. So AI is the big umbrella. We're trying to program systems. Machine learning is a sub umbrella where we try to teach machines how to do tasks by using pattern recognition. And eventually we go to deep learning, and what deep learning is, we're trying to use neural networks. And the simplest thing of understanding a neural network is just by looking at our brains. For instance, we have senses. If you touch a cup of coffee, you can tell it's warm because you can touch it. You can feel it, you can smell, you can listen. All these senses allow us to understand phenomenon. And from there we can apply some kind of a predictive manner or analysis to see how we can go from there. Now, one of the fundamental things about AI, which we hear a lot from my students, plus a lot of colleagues, is the fundamental concept is we have an algorithm, and an algorithm, you want to think of it, it's basically a set of rules that allow a certain, let's say, computer program to behave in a certain manner when it sees data. if you have a bunch of algorithms together, we call this ensemble. So ensemble is a group of algorithms either working together or against each other to try to solve a problem. We also have surrogates. So surrogates can be as simply as a very simple algorithm that tries to explain what a complex algorithm is trying to do. And finally, we have different types of algorithms. Analysis. You have supervised learning, unsupervised learning, reinforcement learning, semi-supervised learning. And as you can see, when somebody looks at this, they say, well, this is way too much. I mean, sometimes it could be a little bit overwhelming. But at the end of the day, if you think of these as opportunities for trying to leverage different components for new systems, it brings in a lot of interesting questions. Now, the thing I would like you to always remember, you can, as an engineer, you can basically develop your own algorithms from scratch, which would be great, or you can use pre-developed tools done by our colleagues in computer sciences and computer, departments. They have done many tools. They have been very well validated across different years, perhaps decades by now. So when it comes to AI, one of the things that I see a lot of people are hesitant of is coding. And in this case, we didn't really have to relearn coding per se, because we have tools that allow us to get to using these important tools. And I wouldn't want you to think that this is one of the limitations, that because I'm too old, like I just finished the school 10, 20 years ago, I'm not going to be using AI. Think of it as a cool thing or as an opportunity to learn something new, just like what this session is trying to do with those 2 hours of learning experiences, right? So we're engineers, we really know how to design experiments, how to go to the lab, fabricate concrete beams, columns, test them. We're also very familiar with using FE simulation, find a difference, find an element. We can build models, as you saw in Abacus, ANSYS, to try to replicate experiments and try to expand upon experiments by using parametric studies. When it comes to AI, it's a similar phenomenon. And as you saw by my colleagues, you have to collect a lot of data, because the goal in AI is to try to train it how to analyze a phenomenon. So in order for it to understand the phenomena, you have to show it a number of examples, and from there it becomes a little bit easier for it to see, okay, well, this is how a beam deflects, this is how a column crushes, and from there the problem becomes easier. Perhaps it's a little bit visualizing, or it's a good exercise to visualize a problem. So as I mentioned, I come from a structural fair background. Let's say we have 2 identical beams. We have beam 1 and beam 2, same size, material properties, boundary conditions. The only difference is beam 1 has a load that's a little bit higher than beam 2. So this is the only difference. Now let's start to make it a little bit interesting. So we're trying to burn these beams. That's what we do in 216. We analyze structures when they burn. Now the first thing that comes to mind is, well, what's going to happen to these 2 beams when they are under fire? Well, the question is, the temperatures are going to start to rise in their cross section, and because the beams are identical, basically the temperature rise would almost be identical because the beams are exposed to the similar fire conditions. However, if you look at the deformation behavior, you would see that beam 1 has much higher deformations at a shorter time than beam 2. And this behavior here tells us that this behavior is a function of the applied loads. If you have higher loads, you're expecting to have higher deformations, which would lead to earlier failure. Now, we know this because we do tests and we can observe that, and we can have now a link between loads and deformation. But in real life, the problem is much more complex than, because we have geometry plays a role, material properties plays a role, loading plays a role, boundary condition plays a role. All these things together are components, and they all have subcomponents components that they interact with each other. So perhaps it's a very complex problem to try to analyze how a beam would behave under fire, because we have all these, subcomponents together. And this is why we do tests, and tests are very, very expensive, and unfortunately may not be comprehensive because we don't have unlimited funds. So a question arises, perhaps if we teach AI the physics behind the deformation of beams, maybe we can develop like an AI of our own that can allow us to figure out how temperature rises and how beams deflect without having to do tests or without having to do simulation, because now AI understands the physics behind this problem. And this is what's going to be interesting once you do that. And once we actually did this at Clemson. So you would see that if you would like to build upon this model, you would see that instead of having, so basically this is a concrete beam. It's been tested in, I think, in 2000 by a group at the University of Ghent in Belgium. And this is the temperature rise within this beam. Now, our goal is to try to figure out the temperature rise within this beam without having to use FE simulation, without having to worry about, mesh, element size, convergence criteria, what simulation software I'm going to be using, and to try to use AI. And once you do that, you can develop an AI code that allows you to come up with this temperature rise at time of firing almost instantaneously, because now we don't have to do a simulation or a test. AI understand the physics. And what's beautiful about this is I don't have to worry about coding, because now I have AI works in the background of this Excel sheet. So basically any questions that arise because I don't know how to code are now away, because now you have a user interface that allows you to do all these cool things without having to worry about coding, what type of algorithm, because everything has been validated for you. Most interestingly, it can also do deformation. So without having to do, to worry about the other items, you can just double click your Excel sheet. Now you have yourself a deformation curve that allows you to figure out how much the deformation of this beam are going to undergo, like within 90 minutes, let's say, of fire exposure. If you would do this in a FE simulation, sometimes it takes a few days to get like a model complete, because you have to worry about what kind of material model, fire condition, boundary condition, what kind of element type, element size, all those things. But whenever you try to use AI, you basically bypass all those hurdles, and now you can have a tool that allows you to do very, very quick analysis within a very small amount of time. If you are thinking about it from an industry perspective, time is resources, time is money, and now you're trying to mitigate a lot of issues when it comes to trying to analyze components. Now, one of the other problems that arises with AI is we call fire-induced spalling. This is a very big phenomenon, and I'm sure you have seen something like this. So basically, this is a concrete column before firing, before we apply temperatures. As you can see, it looks very nice. It's unique. And after fire, you can see the cross section has lost a lot of size, just simply because of spalling. Now there is a lot of theories behind spalling, and it's very hard to explain all of them here. But at the end of the day, whenever spalling happens, as you can see, your cross section becomes smaller. Smaller cross section means lower capacity, as you know. And you can also see that we lose concrete cover. And if you lose concrete cover and if you have fire, this means that the member will be heating up very, very quickly. That's one. Two, reinforcement will also be heating up as quickly as well. So basically you have lower capacity and faster rise in temperature, which become very, very dangerous under fire conditions. Now, as you can see, this small video is taken from University of Sheffield. You can see this is what spalling looks like. So basically, it's a big chunk of concrete will just fly out whenever you heat concrete. And if you think of this problem from a fight first responder perspective, they all have to go into buildings. They have oxygen tanks. If those is concrete covers, they would, God forbid, scratch a oxygen tank or like cause the damage, it would cause a lot of losses, which is something that we don't want to see. We also see this a lot in actual cases. This is I-85 in Atlanta, I think 2-3 years ago. Once the bridge collapsed, you can see that there is a lot of spalling happening within the concrete piers as well as within the girders. So all these phenomena of spalling brings in a lot of questions. How can I predict that? What can I do to prevent concrete from having this, unfortunately? So if you do some research literature, you will see that there is a lot of work on spalling, almost 11,000 papers, as you can see here. Some of the notable ones are listed here too, so you can always go through them and try to see the different types of methods they used to develop tools to try to predict spalling. And once you dive in deeper and deeper, you will see that these tools are very complicated just because the phenomena is complicated. It's not because we don't know why, it's because it's very, very hard phenomena to predict. So one of the question arises is, can we use AI to try to figure out if we can predict this spalling, perhaps, right? Let's see what AI would tell us. Maybe it would be able to give us a quick solution for this problem. So the first thing is always go, read your literature, understand the problem, and you would see that fire is actually, our spalling is a function of aggregate type, fiber content, strength of concrete, humidity, moisture content, magnitude of forces, boundary condition, fire intensity. There is a lot of items that come into place. And as you can see, because you have a lot of items, the phenomena is complicated. And this is where it could be interesting to use AI. So what do? We try to apply different AI methods. And what we came up with actually was interesting because now we taught AI how spawning occurs. And again, we didn't have to go through the whole problem of trying to develop a very black box, for instance, or a complicated tool. We developed a very simple app that anybody can access, anybody can use. And it's of course, it's a free app. You can plug in all these parameters here, you can change it. And the app would be able to tell you, well, this phenomena here is going to have, or this column with these parameters here, or it's going to have a spawning with, for instance, a minor probability, major probability. Is it going to be a big, larger component of spawning? As you can see, no spalling or yes spalling, major or yes spalling for minor. So it tells you this concrete mix under these conditions is likely to have a spalling. So now at least you have a tool that can allow you to figure out, maybe I should go back and try to manipulate my mixture design a little bit just to try to negate the spawning phenomena because I don't want to have it. One of the other things that we also found interesting is this. So this is how an autonomous car actually drives. This is how I understand this is a vehicle, or this is like a person, or this is a traffic light. If everybody uses an iPhone, the first thing you would do is you would turn on your Face ID. So this is how your iPhone knows, well, this is my face. So if you see me, please unlock the phone. And I saw this very cool study done in Europe where actually some researchers, they tried to see, well, if Mona Lisa was a person, how would it talk, or how would it interact with other people? So all these three different examples shows you how we can use AI in different fields. And this is what we call computer vision. So computer vision is basically an AI algorithm or technique that allows computers to understand what visuals mean. Now, if I can teach a computer to understand what a vehicle means, or the different faces of ours, of how Mona Lisa can talk and behave, perhaps I can also allow it to use its logic to understand spawning. And what we did here was actually very, very cool, because what we found, it's AI is like a language. It's very intelligent. So for instance, if you have a scenario like this where you have a fire in the building after the fire, so what we do is we send out engineers to go back and see, well, how much damage do we have? Well, now we can use AI to tell us, well, this component here has a lot of spawning, and this is my confidence. So AI can even tell you if it's confident or it's not confident, and it's trying to analyze, when it analyzes something, a picture or a video, they would say, okay, well, this is a minor spawning. As you can see, you don't see reinforcement here, which means concrete cover is still almost there. In this case, this is major. We have a lot of reinforcement. In this case, it's mild. There is almost nothing. So not only it can tell us that, but it can tell us how much residual strength do we have. And remember, this is all done autonomously without having to have people going back and tagging these pictures. Because now AI, once you teach it, it understands what those things means. It's also, and because it's human free, it's very safe. So basically, once, God forbid, something happens, you can send out a drone or take some pictures remotely. So you can analyze those damages without having to worry about sending people into a building that we don't really know if it's going to be safe or not. It's very quick, and because it's quick and safe, it's very cost effective. So this brings me really to the final slide. I mean, it's the end of my presentation. And from here, it says where to go from here. As you saw, I'm trying to reminisce on my colleagues has mentioned. Experimentations as a great has been working for us for a long time. This is how we came up to here. FE simulations are also great because it allows us to extend the physical tests. AI could be a new gateway for us that we can leverage and apply in lieu or even in parallel with the other two methods, because it allows us now to extend even further with very, very low costs and try to figure out what data tells us, what observation actually tells us. If you think of it, when we do a test, we actually see the test. The observations from our test reflects the physics. In this case, we have massive data points that we try to see if we can get some physics out of it, in a way. Of course, without having, we always need support from industry, academia, because things go hand in hand. As Henry mentioned, I know UCLA they have a course on AI, and we also have one in Clemson on AI as well. So when it comes to structural engineering specifically, so as you can see, then our new students are going to be graduating, 5-10 years from now. They're going to be having a lot of knowledge on AI. So you would expect things to start to change very, very soon. We might as well start to use, to start jumpstart things as opposed to waiting to have to deal with everything as the construction industry, unfortunately, is famous to do. And the future is AI really, because robotics are using AI, medicine is using AI, NASA is using AI to figure out different planets and how we can land on the moon and Mars. So if we can just use a little bit of AI in our industry, it would be substantial. It would help us a lot, hopefully. And finally, of course, thanks to ACI, thanks to the panelists, thanks to the authors of our SP, thanks to the chair of 216, 444, and 544 for co-sponsoring this seminar and this session. This was a very big effort to group, and I'm very happy to be part of it. And I'm glad to get to know, all of you together